Sometimes just one single experiment can completely flip our understanding of reality on its head. Today, we're talking about one of those moments. The experiment that took this kind of weird, abstract idea about light and proved with the clean, simple logic of a billiard ball collision that the photon was very, very real.
Okay, so let's kick this off with a really simple question. We all know what happens when a ball bounces off a wall, right? But what about light? What happens when something like a high-energy X-ray smacks into an electron and bounces off? 100 years ago, the answer to that very question broke physics wide open.
All right, let's set the scene. It's the early 1920s, and physics felt, well, pretty much solved. You had Newton, you had Maxwell, the big laws were supposedly all laid down. But deep in the labs, some really strange clues were starting to pile up. And one of the most stubborn ones involved what happened when you fired X-rays at a simple target, like a block of graphite. And this is where the real mystery starts. See, based on everything physicists knew about waves, the scattered X-ray should have the exact same wavelength as the one that went in. But that's not what the experiments were showing. The X-rays that bounced off actually came back with less energy, which means a longer wavelength. They came back, so to speak, a little bit redder. This bizarre, totally unexplainable result was named after the guy who so carefully measured it, Arthur H. Compton, and it became known as the Compton effect. It was a serious puzzle that classical physics just had no answer for. So why was this such a huge deal? I mean, why couldn't the old trusted laws of physics explain this away? Well, let's take a closer look at why it was such a problem. The classical idea, the one based on wave theory, is actually pretty easy to picture. Imagine an incoming X-ray wave washing over an electron. It should just make that electron jiggle back and forth, oscillate, at the exact same frequency as the wave that hit it. And that jiggling electron would then radiate a new wave, but it would have to have the same frequency, the same energy. It was a totally closed loop, no energy loss allowed. This quote right here just gets right to the heart of it. This wasn't some tiny error in the math. The fact that the wavelength changed at all fundamentally broke the theory. The most powerful, most established theories of the day were completely, totally powerless to explain it. And this is where Arthur Compton comes in with a genuinely radical idea. He decided to just throw out the old playbook. He proposed a model that completely broke with 100 years of thinking about light as this pure, perfect wave. His idea was simple, almost shockingly simple. He just asked, what if this isn't about waves at all? What if light is actually a particle? And what if this whole thing, this whole interaction, is just a straightforward two-body collision? Like one billiard ball hitting another one. To make this work, Compton grabbed an idea that Albert Einstein had proposed way back in 1905 for something else entirely, the light quantum, which today, of course, we call the photon. And here's the crucial part. This particle of light didn't just have energy. It also had momentum. It could actually pack a punch. The real beauty of this model is just how simple it is. Compton just took the two most basic fundamental rules of any collision in physics: conservation of energy and conservation of momentum. He treated the photon and the electron like two tiny billiard balls and just did the math. And the result just pops right out. In this collision, the photon ball smacks the electron ball, transferring some of its energy and momentum. The electron recoils, it flies off, and the photon, which has now lost some energy, keeps going, but with a lower frequency, which, of course, means a longer wavelength. The model perfectly explained, at least in principle, why those scattered X-rays came back redder. But look, a great idea isn't enough in science, right? You need proof. And Compton didn't just come up with a theory. He designed this brilliant experiment to prove it beyond any shadow of a doubt. So this was his setup. He used what's called a monochromatic X-ray source, which just means it produces a single, very specific wavelength of light. He fired these at a graphite target. And the key piece of the puzzle was this thing called a crystal spectrometer, which he could rotate to precisely measure the wavelength of the X-rays that bounced off at all these different angles. Now this is the absolute kicker. Compton's billiard ball model didn't just give a vague story. No, it gave a precise mathematical prediction. This very formula you see here. It predicted exactly how much the wavelength should change, based purely on the angle it's scattered at. The more the photon got deflected, the more energy it should lose. It was a totally testable hypothesis. And this is that aha moment. When Compton actually ran the experiment, the data he measured matched the predictions from his formula perfectly. At 45 degrees, at 90 degrees, at 135 degrees, every single time, the reality in the lab confirmed the simple, radical particle collision model. So just like that, the puzzle was solved, the verdict was in, and the implications were about to completely reshape our understanding of the entire universe. This wasn't just another data point. This was the moment the photon stepped out of the shadows of weird theoretical physics and became real. By showing that this light particle conserved both energy and momentum in a collision, just like a real physical object, Compton gave it legitimacy. It was conclusive proof. The photon was real. Now, Compton's discovery didn't just happen in a vacuum. I mean, this timeline really shows how this quantum idea had been building for more than 20 years. Planck got the ball rolling, Einstein provided more evidence with the photoelectric effect, but it was Compton's 1923 experiment that delivered the undeniable smoking gun evidence that finally sealed the deal. And for this absolutely revolutionary discovery, for proving the reality of the photon, the scientific community gave its highest honor. Arthur Compton was awarded the Nobel Prize in Physics just 4 years later, in 1927. But the story didn't end there. Like any truly great discovery, the Compton effect just opened up whole new fields of questions and led to an even deeper understanding of the quantum world. Yeah, this discovery had immediate ripple effects. I mean, shortly after Compton's announcement, another physicist, C.T.R. Wilson, actually managed to capture images of those recoil electrons, giving direct visual proof. The theory itself got an upgrade with the Klein-Machina formula a few years later. And, of course, this fundamental understanding of how photons interact with matter led to practical applications we use all the time today, from designing radiation shielding to making medical imaging possible. So, we end here. Compton's experiment proved that light, something everyone was sure was a wave, could act just like a particle. And this raised a fascinating and profoundly important question that would drive the entire next phase of the quantum revolution. If a wave can act like a particle, could a particle maybe act like a wave?